So in lesson 1.1, we talked about Riemann sums. In lesson 1.2, we're going to talk about a new thing called definite integrals. And what we're going to do is we're going to use definite integrals in terms of limits of Riemann sums. Now, here's the thing. When we are calculating Riemann sums, we are using very simple geometry formulas. The formula for the area of a rectangle to try to approximate the area under a curve. Now, what a definite integral is going to do is it's going to try to calculate the exact area under a curve. And so what we're going to talk about real quickly is the definition. So if I want to know the area under the curve f of x between x equals a and x equals b, I can take the limit as the norm of the Riemann sums goes to 0. So remember, the norm of a Riemann sum describes the widest rectangle. So as the widest rectangle gets smaller and smaller and smaller, as in as the widest rectangle goes to 0, the Riemann sum is going to get better and better and better of an approximation of the actual area. Now that's one definition of it. We don't use that definition a whole lot, but it does make kind of sense. Now, a slightly different definition means the same thing, but says it in different language. Says that, again, the definite integral, the area under f of x from x equals a to x equals b, can be approximated as the limit of n, which is the number of partitions, the number of rectangles, approaches infinity. So the more rectangles that I use, or the skinnier, the smaller the rectangles that I use, like I said, skinnier, the less wide rectangles that I use, the better the approximation is going to become. And in this case, this second formula, we also have a little bit more information. In this case, delta x right here, delta x, remember, being the width of the rectangle, is found by taking b minus a over n. This is for a regular Riemann sum where all of the rectangles have the same width. Again, this would work for any Riemann sum because we're talking about the norm here. In this case, this is a regular Riemann sum. And c sub I is defined by the formula a plus I times delta x. Now we're going to come back to this formula in one of our later examples, but I wanted to just kind of explain what we're talking about here. And I actually went ahead and drew up a nice little pretty graph, okay? So in this graph, we have the function y equals x cubed minus 6x squared plus 8x plus 4 from x equals 0 to x equals 5. Now, if you notice, the bottom is split up by every quarter, so it goes 0.25, 0.5, 0.75, 1, whereas the y-axis is split up by half, so 0.5, 1, 1.5, 2, etc., etc. So it's not exact in the way it looks. And besides, I graphed it by hand, so it's not going to be perfect. So now let me show you what these Riemann sums kind of look like. And I'm going to start off with just one rectangle, where its width is from 0 to 5. Now I use the midpoint rule, so it looks something like this, okay? So like I said, the rectangle goes from about 0 to 5, and there's the midpoint at 2.5, and that's the rectangle that's used to approximate it. Now, I'm imagining you guys realize that's not a very good approximation. So instead of how about using one rectangle, let's try using two rectangles. Now again, this is a regular Riemann sum, so it's split into two even rectangles. 2.5 is the middle place. Again, I use the midpoint to determine the height of the rectangle. Now, I'm sure you guys can agree that this is better than the first one, but it has a long way to go. We have this big extra section where it's above or has an overestimate here, but it's also got a little bit of an underestimate here. This is way an underestimate over here on the side. So there was 2. Let's bump it up and look at 3, okay? All right, here's 3. Still a little bit better, not perfect, but a little bit better. So notice again, still using the midpoint rule. So we're starting off here at the top, and we're following it as it comes down, and it goes back up a little bit at the end. Still not great. Let's try 4. All right. That's much better. Again, we're starting off kind of high up here, going down and then coming back up. All right, so that's 4. Let's try another one. Let's do 5. All right, still, look at this. We're getting slowly better. Still, we're having a bit of an overestimation here. Not bad estimations in here. Still a bit of an underestimation over here on the right. All right, so that's 5. Now, I'm going to do one thing. Notice we were getting better as we went up. I'm going to make a big jump now, and I'm going to go from 5 to 10. Now look at that. That's much better approximation. We have very little that's over. We have a few spots, but not much, but we also have very few unders. If they are under, it's not by much, except right here at the top. Now, notice I'm not exactly perfect. I had to cut these rectangles by hand. I'm going to do one more. So notice I went from 5, which was this, to 10. I'm going to do one more. This one's going to be the best one. All right, I got 20. Now look at that. I would say that out of all of these, the 20 is probably the best approximation because there's very little that's above or below. It's really, really close. It follows the function very well. Now let me repeat again. What's happening to these rectangles as my approximations get better? Well, the rectangles themselves are getting skinnier. The norm of the rectangle is getting smaller because the width is shrinking each time. The other thing that's happening is we're also having more and more rectangles to cover the same interval, the same x value, from 0 to 5. So let me repeat again. The first definition we had was that the rectangles are getting smaller. The other definition said we're getting more and more rectangles. So even though they look different in reality, they're meaning the same thing. And here, right here, is my definite integral, where I'm finding the actual area underneath this curve. Again, where I had 20 partitions, it's not bad. It's pretty close. What do you guys think? All right, so again, that's my explanation of the definition of a definite integral in terms of Riemann sums. We'll be back with some examples in a second.